Let's get started with this thing. The first few sessions in this course are more theory than practice, because to be able to start modeling time series, we need to have first the background on some of the theory behind, so that we can understand why we use certain tools to try to determine what type of model is the one that's appropriate to the series that we have at hand. So I'll be going over this presentation is ST02 Statistical Foundations. So let's get started with this thing. As you know, in inference, what we do in statistical inference is we try to draw conclusions about a population based on a sample, okay, on a sample from that population. That's what we try to do in statistical inference in general. Now, what's the population in a time series? In time series, the population depends on the type of analysis and the type of model that we are trying to envision. We talked about last time about decomposing a series in terms of trend, seasonal, cyclical, and irregular. And this approach in particular is aimed at estimating only the different components, the trend component, the seasonal component, and so on, okay? This approach that we discussed last time, when we decomposed the series in its trend, its seasonal behavior, and its drawing in the noise part, is not aimed at making inferences. It's aimed at estimating what the seasonal component is. And in most cases, in particular, economists use this approach to deseasonalize time series, to remove the seasonal component of the time series. Now, what we're going to study in this class is the stochastic approach, because stochastic approach gives us a lot more flexibility. There's a larger number of practical situations that can be modeled if we use this stochastic approach. So that's why we are going to be centering in this stochastic approach in the class. And we'll be viewing that any time series as a realization of a stochastic process, okay? Now, you already took stochastic processes, but remember, a stochastic process is just a family of random variables associated to an index. And that index is just a set of real numbers, could be a set of integers and so on. But that's the stochastic process, a family or a sequence of random variables, let's say. So let's think of these random variables as z of tau, where tau is in some set capital T of indexes. Okay, and that'll be a stochastic process if this index set T again could be a continuous interval, or could be just a bunch of numbers, a bunch of integer numbers. If T is an interval, then we say that the process is continuous. Okay, so if we can have the values for this random variable at any point in time between time 0 and time let's say a year from 0, in any instant of that period of time, then we will say that's a stochastic process continues. If T is finite, if it's T finite, it's a numerable set or infinite but numerable. Okay, doesn't have to be necessarily finite, but could be infinite by numerable, but numerable. Then the stochastic process is said to be discrete. Okay, because we only have values for a random variable at times, let's say time 1, 2, 3, 4, and so on. Okay, time 0, time minus, okay, which would be the current time t minus 1, t minus 2, t minus 3, and so on. So it's a numerable set in essence when we talk about a stochastic process that's discrete. Now, whether the process is discrete or continuous doesn't have any implications about the random variables. I could have a continuous process in such a way that the random variable z is a discrete random variable. So at any point in time, c can only take a numerable set of values, let's say, or z could be continuous also. So one thing is the nature of stochastic process, and the other one is the type of variables that are involved in this stochastic process. We'll be dealing with time series. We'll be dealing with discrete time series because that's the models we're going to be looking at are aimed at modeling those types of data. And normally we see observations at some finite number of periods of time. It's cases where we have streaming data, for example, where the variable may be continuous or discrete. For example, I can have streaming data. Imagine data that's coming from a sensor that's measuring the viscosity of a chemical process. Okay, that sensor is continuously making measurements. Okay, so I could think of that stochastic process as a continuous stochastic process, but I'm going to observe it at discrete times. Okay, I will observe the viscosity and check the viscosity. I cannot be checking the viscosity continuously, although the data comes continuously. Normally, we'll check it every 5 minutes, every 10 minutes, and so on. Unless we have a model that can take the streaming data and use that streaming data to forecast where going to be where the process is going to be sometime from now. So, but the nature of the variable is discrete or continuous, and the process can be continuous or discrete. And of course, we will be dealing with stochastic processes that are discrete, and we'll see how they can be discrete. Okay, a discrete time series is a time series which is generated by a process where the index set is time related. Okay, because I can have in this previous slide that we saw, it doesn't say anything about this thing. It's any set where tau belongs. Okay, and this could be coordinates in a coordinate system. So I could be my random variable could be measured at different locations, and then my series node would not be a time series, would be a spatial time series. Okay, we have a series that is that's related in space, a spatial series. No? But we'll be dealing here with time series. That is when the observations from that are generated by that stochastic process are related to time. So we observe data at different periods of time. And we will be making inferences. We said earlier that the purpose of statistical inference is to make inferences about a population. Well, here we will be making inferences about the stochastic process. Okay, making inferences about the characteristics that correspond to a stochastic process that generated a particular series. So we'll think of each series that we see, each time series that we see in practice, we'll think of that time series as a realization of a stochastic process. Okay. So we will only consider discrete time series with observations made at equal time intervals. Okay, that's the type of models we're going to be considering. We have observations in time, and the time intervals where we have the observations are the same. If it's daily, it's daily data. If it's weekly, it's always weekly. And if it's monthly, it's always monthly, and so on. Since we're dealing with discrete time series, we will denote by Z1, and even if this discrete time series can go forever, okay, because the set of indexes here could be infinite but numerable, we only observe a finite number of those of the realizations of that process. So we will use Z1 through Zn to denote pick any origin tau 0. Okay, so Z1 through Cn, to simplify notation, since the time intervals are going to be the same, we may be observing data at the time C tau 0 plus H, Z tau 0 plus 2H, T Z plus tau 0 plus NH. H is always constant. Okay, so we're looking at constant increments in periods of time. So we'll simplify the notation by just denoting by Z1 through Zn. These are our n observations that are equally spaced in time. Now, how do we generate discrete time series? Could be by sampling. Okay, for example, the monthly inflation rate is measured through the consumer price index, is obtained at the end of each month. Okay, so it's by sampling. That's one method. In a chemical process that I was talking earlier, I have a sensor that's measuring viscosity constantly, but I only choose to look at the measurement that I took every hour. So I look at the end of the first hour of the process, measure the viscosity, at the second hour, measure the viscosity, and so on. We could also get at a discrete time series by aggregation of a continuous time series. Okay, for example, a monthly amount financed by commercial banks is an aggregation of the amount financed at the end of the month. Okay, if you consider all the banks, just say in Mexico, well, all the banks are constantly financing amounts at different periods of time. And so I could consider that a continuous stochastic process. But I only observe what I measure here is the aggregation of all those amounts financed by the different banks. And I look at that amount financed at the end of the month as the aggregation of those observations in all the banks any period of time during the month. Okay. So that's the two ways that we can get a discrete time series. Now, as we mentioned earlier, the discrete time series is the realization of a stochastic process. And the thing that we do not know is which stochastic process generated the series. And that's what we want to make inferences about. What is that stochastic process that generates the series? The behavior, we know that the behavior of any random variable is characterized by its density. If it's a continuous, let's talk about continuous random variables. Okay, it's characterized by its PDF, its probability density function. Okay, so if we have a sequence of random variables Z1 through Zn, then the behavior of that sequence of random variables, which is the realization of a stochastic process, is the joint density of Z1 through Zn. Okay, so it's the joint PDF of Z1 through Zn. In general, the stochastic process that's associated with n random variables can be characterized by their joint PDF. Okay, that's going to be in general the case. If the variables were discrete, then we would be able to generate it by the joint probability distribution, right? For each point, we'll have a different probability, but we will be dealing with random variables that are continuous. The type of things that we're going to be modeling here are sales, are temperatures, are inflation rates, let's see, exchange rates, and so on. So all those variables are continuous random variables. So we'll be talking about the joint PDF. Now, as you can see, finding out the joint PDF of a bunch of random variables given a sample is not easy. It's not something that can be easily done. Because in particular, in time series, we assume that there is correlation among the observations in these random variables. In the statistical methods, you saw that we also assume independent random variables, right? There's always the independent, identically distributed random variables. If these were independent, then the joint density functions, the joint density function of Z1 through Zn, if they were only independent, that would be only the product of the density functions from Z1 of Z1, Z2 up to Zn. That would be the joint density function if they were independent. But in time series, data are correlated in time, so we cannot assume independence. That's why estimating this density function becomes a complex matter. Okay. Plus the fact that we usually have our realizations in time series analysis are large realizations, and says that this n will have to be large. Okay, we have a long history of data. Now let's introduce a couple of operators that are going to be used in the course. One is the backshift operator. The backshift operator is denoted by B, by capital B, and it's when we apply B to Z, to a random variable Z at time t, what we get is the random variable Z at time t minus 1. Okay, so if we apply the backshift operator to Z sub t, we obtain Z sub t minus 1. So it just tells us take the previous observation. The square of backshift operator, we just apply the backshift operator to the backshift operator of ZT, and that's CT minus 2. Okay, so and if I have the kth power of the backshift operator, we get CT minus K. Okay, so that's, instead of looking at what that operator when that operator acts on our time series, it looks at one lag behind or two lag behinds or K lags behind. So if I denote here a random variable xt as the backshift operator applied to ZT, and YT is B, then this xt will be ZT minus 1, right? This is ZT minus 1. I didn't write it down here. But this means that this new variable xt is CT minus 1. If I take YT as B to the 12 ZT, that will be ZT minus 12. For example, if I have monthly data, then YT would represent the observation from the previous year, the same month, the previous year. Okay. For example, the consumer price index at time t, if I look at the backshift operator, let me see. Let me see if I find the file. It's opening the file. Okay. At least it found it. It's too slow. This Excel file is also in your in Brightspace. No, I'll give up. Now it doesn't want to do anything here. Now I cannot even leave the presentation. I'm gonna have to abort PowerPoint and restart it. Now was here. Let me open the link from here and see if I can open it here from here. Open link. Well, I cannot open it, but if you have a file there, essentially it just shows the consumer price index and show, okay, here it is. So the backshift operator, all it does, see here's I defined XC to be the backshift operator to apply to CT, right? So if CT is my CPI, let me hide columns that I don't need here. I'll hide all this that I don't need. So I have, this is my variable XT, which is the backshift operator to apply to ZT. And so I have a missing value here. I don't have a value for the first data point. And then I have 0.1143, which corresponds to CT minus 1 and so on, okay? Notice what happens when I look at the 12 power of the backshift operator. I actually lose 12 observations, right? Because I have my observations start at January 1992. So if I need to apply the backshift operator to the 12th power, I need to take CT minus 12. So I lose these first observations, and this is my new series. This is YT. Okay, this is YT. Okay. Now, another operator that we'll be constantly using here in the class is the difference operator. This is written like the inverse delta in the inverse capital delta, and that is when I apply the difference operator to CT, I obtain CT minus 1. So I take CT and subtract CT minus 1. I can write this thing, the backsheet, the delta, the difference operator is essentially 1 minus B, right? It's when I apply 1 minus B to CT, I get CT minus 1. Okay. If you look at books and economics and econometrics, in econometrics they use this difference operator, and in econometrics they use this difference operator equal to CT plus 1 minus CT. It's essentially the same thing, just different notation that they normally use in econometrics books. But we'll be using the difference operator like defined as apply a difference to ZT, it's CT minus 1. If I apply a second difference, it will be the second power of the difference operator. This is 1 minus B squared applied to ZT. That's 1 minus 2B plus B squared applied to ZT. And that will be, gave me ZT minus 2CT minus 1 plus CT minus 2. So that's the difference operator applied 2 times. And in general, if you can use induction to show this thing, that the kth difference, the kth power of the difference operator, or we usually say this thing as the kth difference of CT. So this will normally call it the kth difference of CT. That will be this, the kth operator applied to CT. Okay, that's the kth difference. That will be 1 minus B to the K applied to the, as an operator applied to ZT, and that'll give me this expression, k factorial divided by j factorial, k minus j factorial, minus 1 to the j, CT minus j. Again, you can prove, you can show this by induction without problem. And if I define the series MT equals to the first difference of CT, which is CT minus 1, what I get, let me go back to the file. Here I have I have MT, which is defined as ZT minus CT minus 1. I take 0.0045, which is the difference between 0.1188 minus 0.1143. Okay, and the next observation here is 0.1231 minus 0.1188. Okay, that's it. That's the second observation, and so on. Okay, that's the first difference of my CPI series. Okay, that's the first difference. Again, notice that what happens is that when I take one difference, I'm gonna lose one observation. See here, I don't have this observation now. If I were to take a second difference, I need, for the second difference, look at this equation here on the presentation. For the second difference, I need CT minus 1 and CT minus 2. So if I were to take a second difference, I would lose 2 observations if I take a second difference. And if I take 12, the 12th difference, for example, if I want to look at the difference between observation t, time t and time t minus 12, okay, then I lose the first 12 observations. But if I have monthly data, let's suppose it's monthly data from sales of a product, it's probably, let's say it's toys. Well, that I will have a seasonal behavior where every November, December, January, the sales are higher than in the summer, for example, in summer months. So I will have to take a 12 difference to detect that seasonal behavior. So that's why we use these operators to act on the time series and be able to use them to model to find the model that will represent the stochastic process. So these are the 2 operators that we will be using constantly. So if a series represents inflation at time t, the difference series would represent the increase or decrease in inflation from time t minus 1 to time t. Okay, that will be the increase or decrease in inflation. Or if it's sales, will be the increase or decrease in sales month to month, the first difference. Okay. We'll be using backshift operators in the form of polynomials. So we'll be talking about polynomials where we'll have some constants. Here, look at this polynomial here: ZT minus G1 CT minus 1 minus GK CT minus K. I can express this thing as ZT minus a sum from J equal 1 to K of G sub J CT minus K. And this I can express shortly with a polynomial that I'm calling here G of B, where I take 1 minus G1B minus G2B squared and so on, and apply that to CT. I get exactly the same thing. Okay, so we'll be dealing with this type of polynomials. There is, let me get out of here for a moment. We will be using some facts from difference equations theory. So there's a video here. No, I removed it because nobody watched that video. I had a video on difference equations, and I did have also a presentation on difference equations, and I removed them from the space because the last two semesters that I taught time series, I realized that nobody was watching the video, so I removed it from there. The video is in YouTube, so it would be nice if I'll put it again to see if any of you are interested in looking at that at difference equations, and I'll restore the presentation also for difference equations. Okay, but and I'll do it later today. Because most of the theory that we'll be developing now is going to be based on the theory of difference equations. So these polynomials are called backshift polynomials, or in Spanish, polynomios de retraso, backshift polynomials, and we'll be using them constantly in the course. So notice when I apply G of B, instead of writing this whole thing, I will just write G of B, apply the CT, okay? And then if I apply this polynomial to ZT, this is what I get. ZT minus G1 CT minus 1 minus G2 CT minus 2 up to minus GK CT minus K. Now, these polynomials, if you recall your courses, your classes in algebra, we have what's called rational polynomials. And we will be working with rational polynomials. So we want to work with polynomials such that any polynomial G of B that we will be dealing with, we want to be able to express it as the ratio of two polynomials. So that will be G of B. It can be expressed as a ratio of the polynomial A of B and the polynomial C of B. Okay, that's a rational polynomial.
I have a question.
Yeah.
The G from the first line, those G's are coefficients or?
Are constants. Are constants.
Okay.
And actually in our models, those will be the model parameters.
Okay.
Okay. Yeah.
And when you express it as a polynomial expression, it's the backshift operator with that same G constant, or like is other G, like from the first line to the second line?
It's the same G from first line to the second line. It's the same G. So when I apply G of B, when I say G of B apply to ZT, apply to CT, I'm taking this polynomial 1 minus G1B minus GKB and apply to ZT. And then what I get is ZT minus G1, and then G1B ZT1, the ZT, right? Which is ZT minus 1. So I'll put it like G CT minus G2 B squared CT minus up to GK B to the K CT. So this one is G1 CT minus 1. This one will be G2 CT minus 2, and this will be GK CT minus K. Does that answer your question, Marianne?
Yes. Yes. Thank you.
Okay. Now, we said we want to deal with backshift polynomials that are rational. Well, for a polynomial to be rational, again, if you remember your classes in algebra, you'll remember that for a polynomial to be rational, it's really dependent on the coefficients of that polynomial. So for a polynomial to be rational, to be able to express it as a ratio of two polynomials, then that is imposing several conditions on the coefficients, on the constants G sub j. The simplest example of a rational polynomial is G of b equal 1 plus GB plus G squared b squared and so on. That goes forever with the absolute value of G, the constant. The absolute value of G is less than 1. Then this polynomial, which it has an infinite number of terms, can be expressed as the ratio of the polynomial 1 over 1 minus GB. Okay. So this is the simplest example of a rational polynomial. If all these constant, if the constant here, which is the same in all these terms, but it's an infinite sequence of terms, has an absolute value less than 1, then I can express this thing as 1 over 1 minus GB. Okay. That is, if in fact this is what? This is 1 minus GB to the minus 1. Okay. And this can be computed only when the G in absolute value is less than 1. So the sequence converges, otherwise it wouldn't converge. Okay. Now, the requirement that G is less than 1 comes from the following argument that has to do with convergence. If I want to operate the backshift polynomial G of b on ZT, so that when I apply GB to CT, I get this sum. And if we are dealing with a series that has a constant mean for every t, okay, we have a series which has a constant mean, then the G of b applied to ZT will be this mean, Z bar, times the sum of the G sub j raised to the power j. And this sum here, this sum will only be finite if G is less than 1. Okay, this sum is only finite if G is less than 1. So if my series is going to have a decent behavior, let's say, then I will need to make sure that there's the sum of the coefficients G to the j are this infinite sum converges, and that's only true if G is less than 1. Okay. This is related to the difference equations theory that is in that video that I will make available in Brightspace. Okay. And I will. There's also a presentation. Let me see. I have it. I don't have it in English, but I'll have I have it in Spanish. Differences, introduction. No, I have it. I have to go look into my previous versions of the class, because nobody was reading that material, so I removed it. But it's related to the theory of difference equations. But this is clear. If ZT has a constant mean, if the data that we are observing, if that mean is constant for every t, then when I apply G, the polynomial, the backshift polynomial G of b to CT, then I would need to get a finite thing. This has to be finite, and to be finite, this sum has to converge, and this will converge when the absolute value of G is less than 1. If it's greater than 1, it will not converge, and I will not have a finite mean for those for that series. Okay, that's the reason behind that, which is actually based on difference equation theory. Now, this notation is helping us, these operators, the backshift operator and the difference operator, are going to help us to express these models that we're going to be studying in a more concise manner, more simple manner. So, for example, one of the models that we're going to see is the moving average model. The moving average model is, we assume that CT, the time series minus its mean. So as you can see, we're assuming there's a constant mean for that time series. CT minus its mean is this theta of B backshift polynomial applied to AT. That's 1 minus theta 1b minus theta 2b squared minus theta q bq, b to the q, a sub applied to a sub t. So what I'm saying here is that CT minus mu is going to be equal to AT minus one constant for AT minus 1 minus theta 2, AT minus 2, and so on, up to CQ, up to theta Q, AT minus Q. That's called the moving average model. Okay. And the ATs we'll see later, we assume that these are white noise. This is an autoregressive model. Okay. This an autoregressive model is of the form a polynomial over a backshift polynomial, phi of b, applied to ZT minus mu. I also subtract the mean for C, equal to white noise. If you let's look at the case to avoid writing that much here. Let's look at the case where P is equal to 1. If P is equal to 1, what this polynomial is saying is that y minus phi1 b CT, and I'm going to call the CT tilde. CT tilde is going to be CT minus mu. CT minus mu. Okay, so I'll be putting the mu there. Equal AT. That's an autoregressive model of order 1. Why is it called autoregressive? Let's write it down in a different way. I put this is ZT. Oops, I moved something wrong with my pencil here. This is CT tilde minus phi1 CT minus 1 tilde equal AT. And I can write this thing down as CT equal to phi1 phi1 ZT minus 1 plus AT. And this looks like what? This looks like a simple linear regression model, right? I'm regressing CT on itself. That's why it's called autoregressive, okay? Because it's essentially the equation of a linear regression model. Remember that a linear regression is a simple linear regression model is y equal beta null. I can have a constant there, doesn't matter. Beta null plus beta 1x plus epsilon plus random error. Well, the ATs are playing the role of the random error, and what I have is a regression of y on x, but in this case is a regression of CT in ZT in the same variable. Okay, so that's why it's called an autoregression. And the autoregressive moving average models will go into detail in these models, in the different models. Okay, the autoregressive moving average model is when I combine both. I have an autoregressive polynomial. This will be called an autoregressive polynomial. This is a moving average polynomial, and I have both. And then when I add the difference equation, I can have a more general model, which is the autoregressive integrated moving averages, which is I have an autoregressive term polynomial. I have a difference, which is the equivalent of integrating integrating back the variables, and this is a moving average polynomial. It's called these are the ARIMA models, autoregressive integrated moving average. So it simplifies the notation of the models, and we can use the theory of difference equations to develop most of the theory for the modeling this time series with the stochastic component, AT. Okay. How are we doing so far? Have I lost anybody or?
No, I think we're okay.
Okay. And swing. Now, we're going to be dealing with linear stochastic processes. We assume that successive values of a time series can be generated by a sequence of independent random shocks, which are, this should be a subindex A sub t, okay? These that I have in here, in the previous line, in the previous slide, these ATs are what we're going to define as white noise, which are going to be random shocks. These random variables are independent, identically distributed with constant variance. So we'll assume that all the successive values of a time series can be generated by a sequence of independent random shocks. Okay, that's essentially what the moving average model says. Because I have a series, let me go back again to this slide. The moving average says that I can generate ZT with a linear combination of white noise, of random shocks. In this case, a finite linear combination. Now, the random shocks that the ATs are assumed to be independent. They are identically distributed with constant mean. And the mean is actually going to be 0. And the variance is going to be sigma squared. It's constant variance. Okay, variance doesn't change with time. That's an important assumption, that the variance of these random shocks is constant through time. AT is known as white noise, and Joule in 1927 proposed to express the time series in this form. Joule in 27, he said, well, any time series can be expressed as a possibly infinite linear combination of random shocks. Okay, the moving average is a particular example of a time series generated by a finite linear combination of random shocks. But Joule in 27 said any time series can be expressed as a infinite sequence or infinite linear combination of random shocks. Certain properties have to hold, and we'll look at those properties. So here I have mu plus AT minus say C1, psi1, AT minus 1, minus psi2, AT minus 2, and so on. And I can write this thing as mu plus psi of b, a polynomial, psi of b of AT. And this polynomial is 1 minus psi1, b minus psi2, b squared minus psi3, b cubed minus psi4, b to the fourth, and so on. Okay, so we'll use the psi polynomial to represent this possibly infinite polynomial with an infinite number of terms, which are y minus psi1 minus psi2. If you see, we keep the same form of the polynomials. The same form in the sense that we are saying, remember the first, we saw G of B, and we said this is going to be 1 minus G1 B minus G2 B squared, and so on. Minus. Okay. This is the form that we'll be using normally. And here I have the same thing. I have psi of b is 1 minus psi1b minus psi2b squared minus psi3b squared b cubed, and so on. That's what Joule proposed in 1927. In an essence, what he's saying is that if you pass this white noise through a linear filter, you obtain a series, okay? Or any series is the result of a linear filter applied to white noise, okay? It's the same thing. And that's for any of the series we're going to be modeling, we'll be able to express in this form under certain conditions that we'll go over now, okay? Now, we know that to fully characterize the stochastic process, we would need to know the joint PDF of all the variables involved. And that, again, is going to be very difficult because we have many variables involved and they are not independent. So it is not realistic to think that we can know what that joint distribution is going to be. Now we see that, for example, you took the normal distribution, the multivariate normal distribution is completely characterized by its mean and its variance covariance matrix, right? Well, since we'll be making the assumption of normality later for the white noise, it will be reasonable then, as you know, the normal distribution is characterized by its first two moments, the mean and the variance, right? In the univariate case. And in the multivariate case, its mean and its variance covariance matrix. So it is reasonable to assume that we can summarize the behavior of the stochastic process that generated the series that we're analyzing if we focus on the first two moments of the series. So we'll be focusing on the first two moments, which are the mean and the variance covariance matrix. Suppose that the means of CT is mu sub t, okay? Suppose that the mean of CT is mu sub t. So in this case, the mean depends on time. Then mu sub t will be equal to mu plus the expected value of this infinite sequence, right? The expected value of this of AT minus psi 1, AT minus 1, minus psi 2, AT minus 2, and so on. To obtain the expectation as the sum of the individual expectations, so to calculate this expectation as the sum of these individual expectations, we require that this sum here, the sum of the absolute value of the psi weights, converges. If this converges, then we can calculate the expectation of this linear combination as the linear combination of the expectations. But that will only happen when this sum converges. Okay? This has to converge. The sum of the psi i's in absolute value has to converge. Psi null is 1, okay? We put it at psi null so that to be able to generalize the equation, instead of going from I equal to 1 to infinity, to go from I equal to 0, from 0 to infinity, we'll make the assumption psi null is equal to 1. Okay. So we need this condition on the psi weights so that we can compute this expectation as the sum of all the expectations of the different terms. And then it becomes very easy. If that is the case, then what can you see from this equation? What would this equation be equal to if I can express the expected, if this is finite, then I can express this expectation as the sum of the expectations, and what's going to be that sum? If this happens, then what is the expected value of AT minus psi 1, AT minus 1, minus, and so on? What is this expected value? Anybody wants to guess?
The A have as mean of 0, right?
That's correct, yeah.
So it wouldn't be 0 because
Yeah.
you're going to multiply it.
Yes, Marianne, it will be 0. It will be
Okay.
0 because it's the sum of the expectations. Since this converges, this will be the sum of the expectations, and the expected value of each one of these terms is 0. Because psi's are constants, they are not random variables. The only random variable here is a sub t, and it has expected value 0. So if this happens, then the mean of the process is a value that doesn't depend on time. Okay? Because if that happens, then mu t is equal to mu, which doesn't depend on time. Okay? So if this holds, expected value of zt is mu, is a constant that does not depend on time. Now, what's the variance of zt? To calculate the variance of zt, we take expected value of zt minus mu squared, right? And then we express zt minus mu as at minus psi 1, at minus 1, minus psi 2, at minus 2, minus and so on. All of these things squared, right? Because ct minus mu is that. Remember that ct minus mu, we said earlier that ct minus mu is equal to at minus psi 1, at minus 1, minus psi 2, at minus 2, minus and so on. Okay, that's ct minus mu. That's a starting model. So this is the expected value of these things are squared. So I take, for example, all the square terms. That'll be at squared psi 1 plus psi 1 squared, at minus 1 squared, plus psi 2 squared, at minus 2 squared, and so on. And then I subtract the expected value of all the cross products. Okay, psi I at minus I times psi j at minus j for I different from j. Okay, from I different from j. This is the square of this sum of this linear combination. This is the square. Now the first term is equal to what? See, look at each of these terms here. We know that the sum of the psi's converge, so the sum of psi squares will also converge, because that means if they converge, that means that the absolute value of psi I for any of I is less than 1. And then the psi, the absolute value of that thing, psi I, when we square psi I squared, that will be also less than 1. So the sum converges, and this term here will be the sum of psi I squared plus times sigma squared. And if we assume that the sum of psi I squared is finite, which will be the case if sum of psi i's in absolute value is finite, converge, then this term here is going to be sigma squared times the sum of psi i's squared. Okay, and this here will be equal to what? One of the assumptions is that the a sub t's are independent, identically distributed. Okay, since they are independent, the expected value of the product, the psi I and psi j are constants, right? So this is expected value. This term here is expected value of the sum. I'm removing the expected value from here. Let me erase this thing. This is going to be equal to the sum of psi I times psi j, expected value of ai times aj. But since they are independent, the expected value of the product is the product of the expected values, and each of these has expected value equal to 0. So this whole term is equal to 0. This part becomes 0. Right. So the variance is equal to this sigma squared times the psi sub j squares, sub I squares. That's only part of the second moment. So we now have the first moment, and we have part of the second moment, which is the variance. We still need to work with the covariances, just the second moment of the series. Okay.
Teacher, I have a question. I didn't quite get why the first term is sigma square A times the sum of these.
Okay. The first term. Let's look at this first term. Okay. Let me look at this first term here. Here we're assuming that the sum of the psi I squares is converges. If it converges, then the expected value of the sum is the sum of expected values. So it'll be, I made it wrong here. Oops. Oh, okay, here. It's a expected value. This will be expected value of AT square plus expected value psi 1 square, expected value of 81, IT minus 1 square, and so on, no? Well, this is this expected value of 80 square. How much is that? What's the expected value of 80 square?
0, no?
No. The expected value of 80 square is its variance.
Okay.
Because that's the expected value of 80 minus its mean, which is 0 squared. That's the variance. So this is sigma squared plus psi 1 squared sigma squared, because the expected value of 80 minus 1 squared is also sigma squared. We assume that the variance is constant. Okay. RID with mean 0 and variance sigma squared sub A. So this is again sigma squared sub A, and so on. Okay.
Okay.
So I can express this, and that's why we made the notation earlier that psi of 0. This is psi 0. This is psi 1 squared. Psi 0 squared. Psi 0 is 1. Okay.
Okay. Thank you.
No, you're welcome. Okay, since we're considering that the time series is a realization of a stochastic process, we should consider all random variables, and hence we need to study the covariance also for it's a second moment. Okay, so we need to study the covariance between CT and CT plus K, or CT and CT minus K. Okay. Remember, the spacing is the same between any consecutive observation. So all I need to look is at the covariance between CT and CT minus 1, CT and CT minus 2, or CT and CT plus 1, CT plus 2, ZT plus 3, and so on. Okay. So we'll calculate the covariance gamma sub K, we'll call it gamma sub K, the covariance between ZT and ZT plus K. I could have done it as ZT minus K is the same. And that is expected value of ZT minus mu times ZT plus K minus mu, right? Because ZT, I can take ZT minus mu and ZT minus plus K minus mu. And we know that ZT minus mu is this expression here in the top. So we have the expected value of these products of CT. This is CT minus mu. This one here is CT minus mu. CT minus mu. There's no subindex here in the CT. CT minus mu. And this one here is CT plus K minus mu. Okay. I'm just computing the product, but expressing it in terms of its linear combination of these random variables, of of white noise. Then, to compute this expected value, I take first all the products of the places where the subindex is the same, okay? So I will have, when I multiply AT, AT plus K, AT plus K minus 1 times psi 1 minus, and then I take the AT, and then I do this thing with AT with all the terms here, the AT minus 1 multiplied by psi 1 with all the terms here, all the products, and what I get is this expected value is minus C sub K AT squared, okay? Because notice when I multiply AT times all these terms, I have AT times AT plus K minus psi 1 AT plus K minus 1 minus psi 2 AT plus K minus 3 and so on, okay? Now, when K is equal to 0, the only term that's common is this 2, this AT, and here it will be AT squared, right? When K is equal to 0. When K is equal to 1, then I will have AT and AT plus K minus 1, okay, which will be AT, that will be AT squared multiplied by psi 1, in this case when K is equal to 1. So I can generalize this thing and see that when K is in general, for a general K, I would have minus, notice what happens when K is equal to 1. If K is equal to 1, the term that I have is what? Is AT times AT times psi 1. Okay, so I have psi 1 times AT squared. That's when K is equal to 1. For all the other cross products that I have here, all the other cross products will be, when I multiply AT by any AT that doesn't share the same subindex in time, that expected value is going to be 0. Okay, those expected values are going to be 0, and I'm grouping them here. This is where I is different from J. See, when the suffix here on this side on the first linear combination with the second linear combination, when the suffix is different, which is when I different from J, I put those terms all together because I know that those expected values are going to be 0. And I only leave the terms where I know that the subindex is going to coincide. So when K is equal to 1, it will only be minus psi 1 AT squared. And when K is equal to 2, I look at the corresponding term here, and this is what I end up with. It's minus psi K, so on. And this is just algebra. This is just algebra. So you can do this thing at home in your free time to have some fun instead of getting bored with other stuff. So you can do the algebra and see that that's the case. So the gamma K, which is the covariance K lags apart, notice that here the gamma depends on K, okay, on how far apart the observations are. And this is sigma squared times psi I, psi K plus I minus psi K times sigma squared. Sigma squared is a constant, and I get that from these AT squares. Okay, and I get this is the sum of these terms. Notice here, for example, this is psi 1 psi K plus 1, psi 2 psi K plus 2, and so on. This is these terms here, and then minus psi 1. I only have one term which is subtracted from the others, where I have one psi only instead of multiplying two of the psi weights. So that's sigma squared times this combination here, which is finite. And that's the covariance between ZT and CT plus K. So it only depends on the separation between the observations T and T plus K. It only depends on K, okay, on how far the observations are, okay? Let's see, I guess I'll just look at this example here. So there's two important characteristics that you should note here before we break and end the class. In this case, where we assume that this sum of the psi weights are converges, the mean is constant, does not depend on time. The variance is constant, does not depend on time. And the covariance is constant, is constant for a given K, okay? It only depends on K. It only depends on the separation between the observations, not on the time when we are placed. That's what that's saying, is that the behavior of the series doesn't really change with time. Okay, the intrinsic behavior of the series doesn't change with time. In this case, we say that the series is stable, or the process is stable. It's stationary. Okay, we'll be using the term stationary when the process first order and second order stationary. This process is considered first order stationary if its mean does not depend on time, and it's second order stationary if its second moments, because it has a variance, and the covariances do not depend on time, which is this case here. This is, for example, an example of a series that is stationary. Okay, stationarity then will be reflecting that the behavior of the series, its mean and its variance covariance structure does not depend on time. Okay, they only depend, in terms of the variance covariance structure, will only depend, the covariance in particular will only depend on the separation in the observations. Okay, we'll be doing more of this thing next time. Stop sharing here.